Hey everyone, my name is Josh. I'm a third year engineering student at the University of McMaster. And today we're going to be going over the Mechanical Engineering 3F04 exam review. This is the start to this series. I made three prior videos that went over the 2023 summer midterm content, which was parts 1, 2, and 3 of the course. I will be adding those three parts to this playlist, along with adding in parts 4, 5, 6, 7, and 8. Just overviews and summaries of these parts. If you want more in-depth content, just look at the course. This is very overview, very kind of trying to get the gist of things in one digestible piece of media. Again, so I'm just going to say this. I'm a student. I'm taking this course right now. I just feel like I have a good grasp on things. So hopefully these videos help. Without further ado, let's start with part 4, optimization. Now, in this course, we went over different types of optimization, and I'm going to be doing the same thing in this video. Now, the types of optimization, the main types were one, we'll say one-dimensional, and two, multi-dimensional or n-dimensional. Now, both of these were under the umbrella using unconstrained optimization or constrained optimization. Now, before we get into this stuff, hopefully you have a brief understanding of what optimization is. Optimization is basically finding the maximum or the minimum of a certain function. Now, the maximum or minimum are your peaks and your troughs. So if I were to draw something like this, right here would be your minimum, the lowest points. Up here, this will be the maximum, the highest points. Now, an unconstrained optimization problem asks you to find the global maximum or minimum, or the global optimum. This is the highest or the lowest point in the entire function. A constrained optimization problem gives you a local optimum. This local optimum is between an interval given. In a one-dimensional constrained optimization problem, it might say find the local maximum, and x is greater than 0 but less than 4. Where is the optimum there? What height's it at? Everything else. We're going to start off this video by giving you guys some numerical methods to solve for one-dimensional. One-dimensional, we'll do unconstrained, because most of these methods are unconstrained, but you can add your own twist onto any of these problems to make them constrained. So one-dimensional, unconstrained optimization problems. Where do we start? Well, like I just said, we're going to go over what an optimization problem is. We know that that's the maximum or the minimum. At the maximum or the minimum, the derivative is equal to 0. So we know f prime at x opt is equal to 0. This is because if we draw the slope of the tangent line at this optimum point, it's a straight line, which we know is a 0 slope. Now we need to know, is it a maximum or is it a minimum? If the second derivative at the optimum point is less than 0, if it's less than 0, that means you're at a maximum. If the second derivative at the optimum is greater than 0, that means you're at a minimum. What I do to remember this is I think of it this way. If I am at a maximum, it's facing down. So the second derivative has to be negative. If I'm at a minimum, it is facing up, which means I have to be at a minimum. Hopefully that makes sense. Now we're going to be talking about the first kind of optimization method. This is a bracketing method, so hopefully you know what a bracketing method is. If not, I'll let you know what exactly it is. So a bracketing method this will pin the maximum or minimum between two specific points. From there, it'll squeeze the maximum or minimum closer and closer together until you're at 1 point. So it squeezes the points together. The first bracketing method is the golden section search method, or the GSS method. Now, I don't think this method's very hard. There's just a lot of if statements and a lot of changing around that you're going to have to get used to. Now, what this does is it pins your optimum between 4 points. XL, which is your lowest X point, XU, which is your highest X point, X1, and X2. Now, what is X1 and X2? Well, the name golden section search is not just a fancy name. It actually comes from the use of the golden ratio in this method. The golden ratio, R, is equal to √5 minus 1, all divided by 2. And that's around equal to 0.61803. Now, we use this golden ratio R to find a specific distance from the X lower and X upper point that is going to narrow down our search. So we call this D, R, the golden ratio, multiplied by X upper minus X lower. We use this D to find X1, which is X lower plus D, and X2, which is X upper minus D. I'm going to use this picture to kind of show everyone what I mean here, or what's happening if you're confused. Now, this diagram shows our maximum. It also shows X lower and X upper. Now, the distance from X lower to D looks like this. This is our X1 points. The distance from X upper to D looks like this. That is X2. Now, both of these points have a specific F value. F of X2 and F of X1. Now, these F values decide what changes in our method. And I'll show you what I mean. Now, these criterion that I'm about to say are specific for finding the maximum of a specific function. So finding max. If f of x2 is greater than f of x1, here is what happens. We're going to call x optimum to be x2. This is because f of x2 is the highest point that we know of right now. What we know, x2 has the highest f. Okay, cool. What this means is, since I know x1 is closer to the optimum point than x upper, I can delete all of this portion of my function. I can forget about it. And I can call x upper, the new x upper new, my x1 old. From here, since I have a new x upper, I need a new d value. So d nu is x upper nu, and I didn't change my x lower, so x lower old multiplied by r. Now here's the cool thing about the golden section search. My x2 is already my new d away from x lower. So I'm just going to make x1 new equal to x2 old, or my x optimum. From here, I can make a new x2, which is just my new x upper minus my new d. Now, we can do the same thing in opposite. If f of x1 is greater than f of x2, this means my x optimum is now equal to the highest point that we know, which is my old x1. I can then delete my entire x lower half because my x2 is both my new x lower since it's closer to the optimum. So x lower new is equal to x2 old. I can make my new d. That's going to be equal to x upper old minus x lower new times r. My x2 new is just going to be my x1 old, since it's d amount away from the one I didn't replace. And then I got to make my x1 new, which is my xl new plus d new. That's finding my maximum. If I want to find my minimum, there's two ways. The first way I can do this if it flips my function about the y-axis. If it doesn't do that, such as a trig function, and it only shifts my function, I can't do this. But if adding a negative to my function flips it about the y-axis, I can just multiply f of x by -1. If it doesn't flip my function, not shift, but if it doesn't flip my function over the x-axis, I can flip my inequalities. By flipping these inequalities, it makes sure I find a minimum. I'm going to move these two pictures, but I am going to need them a little bit later. Okay, now to find the error, it's a lot different, not a lot different, just a little bit different than what we would normally do. To find my approximate error, I have to take 1 minus the golden ratio and multiply it by x optimum. Actually, sorry, not x optimum. X upper minus x lower, and then divided by x optimum. And obviously multiply that by 100%. That is how I find my approximate error. Fantastic. Okay. All right, let's turn our attention now to parabolic interpolation. Now, I'm going to pull that one picture that I moved. Perfect. To use my parabolic interpolation, I need 3 initial points. I'm going to need x0, x1, and x2. What this method does is it fits a parabola to these 3 points. From there, I find the maximum of that parabola, or minimum if needed. From there, I will fit another parabola to my new 3 points until I get close enough to the true value. Now, we're looking at this picture here, my x0, my x1, and my x2. I now have to find my x3. X3 is a very large equation. I'm just gonna pull it. Okay, my x3 equation is here. Very lengthy, but it ensures the x3 that I'm finding is the maximum of the parabola that we just interpolated. Now, my next step are the if statements. If my x3 is at a spot on the x-axis greater than x1, then here's what happens. My new x0 is going to be my old x1. My new x1 is going to be x3. And x2 is the same. What happens if x3 is at a spot less than x1? Well, x0 is the same. x1 new is x3. And x2 new is x1 old. So you can see here, x1 is the only one that's moving and replacing. Okay, so whenever I find x3, my new x1 is always going to be the x3. The condition is just to change what x1 is. X1 can be the new x0, or it can be the new x2. The x1 cannot be x1 twice. Now, my error is absolute value of my new x1 minus my old x1 divided by my new x1. In other words, you could also say that my approximate error is x3 minus x1 divided by x3, right? Since x1 new is my current x3. Perfect. All right. Now we're going to be going to the only open method in this part, at least. So open method. This one is the Newton's method. This one's very simple if you remember root finding. So we remembered to find a root, we use the Newton-Raphson method, and that said xi plus 1 is equal to xi minus, or sorry, not minus, plus f of x divided by f prime of x. We're going to use the same scenario, but we're going to change for x. We're going to change our f's. I'm going to say g of x is equal to f prime of x. Now, our equation looks like this. And I iterate until my approximate error is less than my criteria. What this means is actually xi plus f prime over f double prime. It's not that bad. That's it. I find my new x1 by iterating. Case closed. So super easy. You can see that our one-dimensional unconstrained methods aren't hard. Now, we're going to get to our n-dimensional methods. And they're also going to be unconstrained. I don't think these are too bad either, personally. So for ND unconstrained, there's two different methods, your direct methods and your gradient methods. The direct methods are not very accurate. They're also non-gradient methods. So there are two direct or non-gradient methods. The first one is a random search. Oh, and by the way, n dimensions is something like a 3D shape. So we're trying to find the maximum of this 3D object. Now, random searches aren't very accurate as they just evaluate f of x, y randomly until you reach a maximum. Not very efficient. Okay, I'm gonna pull this picture back up because it has to do with our direct methods. Now, the second one is univariate or pattern searches. They're both not that accurate, but they're obviously better than a random search. So our univariate method makes us move along one variable until the next level is hit. From there, you move along your second variable. That's exactly what this drawing is doing here. You're moving on the x variable until you reach a new level. Then you move along the y variable. Then I move along the x since I've hit the new level. Then I move along the y, then the x, then the y, and so on until I reach a maximum. Now, these dashed lines here on this image represent the patterning method, which is kind of out of the scope on the course. So I'm not really going to talk about it. Now we're going to touch on gradient methods. This one isn't too bad. So hopefully you know that a gradient of a function tells you the direction of the steepest ascent. So if I were to have f of x and I were to take the gradient of f, this turns my f into a function. The derivative of f with respect to x in a vector I direction plus the derivative of f with respect to y in the vector j direction. And the regular gradient f shows us steepest ascents. Or in which direction which direction f increases the most. If I want the steepest descent, I'm just going to take the negative gradient of f. Now, to find out if I am at a maximum or a minimum, I will take the Hessian. It has a special symbol. It kind of looks like an absolute value h. And that is equal to, it's not an absolute value. So remember that. This is the Hessian. Now, if the Hessian is less than 0, You're at a saddle point. At a saddle point, there's no max or min. You're kind of at a stagnant point where if you were to have maybe like a piece of paper, this piece of paper is kind of turned in a way that there's no really minimum or maximum. You're kind of just at an inflection point almost. Now, the Hessian for these next criteria has to be equal to 0. From here, if the second derivative with respect to x is greater than 0, just like in one-dimensional, you got yourself a minimum because of the same reason. If the second derivative of x is less than 0, well, you got yourself a maximum. The same rule applies. Now, in order to find an optimal point using a gradient, you have to walk in a certain direction and then reevaluate. Now, a lot of the times we use what's called the optimal step size model. You might be given a step size, which is great, and you can kind of do this in a couple steps. You can find your x new and your y new in a few steps, but we're going to go over the optimal h or step size. H is step size model. What this does is it creates a function of h to find out what the best step size is, or for how long you should walk in this gradient direction until you can change your gradient direction to find a better way to get to the optimum. Think of it like a mountain, right? I might be on the best trajectory to get to the top, but then I'm going to have to walk around the mountain a little bit to get to the next best point. So to get this step size g of h, I equate it to my function x, xi plus the derivative of f with respect to x multiplied by h. And then for my y variable, yi plus the derivative of f with respect to y times h. Your only variable that you'll have is h. This leaves you with f a plus bh and then c plus dh. From here, you're going to solve your function, and then you want to know what the optimal h is, or h star. To find h star, you're going to take the derivative of g. You're then going to get g prime as a function of h star. All you have to do is solve for h star. There you go. You got your optimal step size. From here, you use that step size to find your I plus ones. Oops. Now remember, your xi plus 1 and your yi plus 1 is equal to the current x or y plus the step size times the partial derivative, or times its gradients, right? Because we're walking in that certain gradient direction for h steps. Now, if you're asked to solve these analytically to find the optimum, you have to set the derivative of your function with respect to x equals 0, the derivative of your function with respect to y, and then solve this system. And with that, closes out part 4. I hope you all enjoyed. Please let me know if you have any questions. Hopefully I can get back to you. Hopefully you learned a lot, and I'll see you in the next video.